Our team consists of 6 members. 3 of us are competing for the first time. They are 50 years, Brent, Murat, and Quentin. 3 of us are competing for the second time, and they are 6 years, Timo, Luis, and I, Eric. We are from VTI Ieper, and we study the same fields, technology, science, and engineering.
So for our primary mission, we will measure the air temperature and air pressure with the BMP 280, and we will collect the data via the ground station with radio communication and the antenna.
The antenna we use is an 1111 Yagi Uda antenna. We already tested this antenna and we received data from 500 meters away. For our secondary mission, we want to change the descent rate of our gunset. How will we do this? We will do this by reefing our parachute. In the center of our parachute, there is a Kevlar wire connected to the DC motor, which is on top of our gunset. This DC motor, this powerful DC motor, can wind up this Kevlar wire, and therefore the shape of our parachute shrinks and we have less drag, so the can will descend quicker. But we can also unwind this Kevlar wire, so the parachute goes back to its original shape and has less drag and descends slower. Now, how is this principle being used? We can to have a quick but safe drop.
For our mechanical and electrical design of the gunset, we first designed it in CAD and Onshape to know if everything would fit. We opted for a really easy access design, so we have easy access to electronics. There is an electronics mount in the middle, in which our battery is seated, and the electronics mount is press fit and later glued into the whole final shell. You can see the motor at the top, which is going to pull in our reefing wire. For the electrical part of the gunset, it's quite simple. We just will use the same ground station as everyone, just a radio module with a Raspberry Pi Pico. We use a big LiPo battery as our main power source with a head master switch and 2 voltage regulators. For the main electronics of our gunset, we use Raspberry Pi Pico as our head processor, a motor driver and a geared DC motor for our reefing, an SD card breakout to store our data, a GPS for location tracking, a BMP 280, and a radio, of course, to communicate with our ground station.
We already assembled everything onto our can, and we will do a fully integrated test in the next weeks.
Our code has 3 stages. The first stage is the arm stage while it's inside of the rocket. It will prepare the reefing mechanism and the collection of the data. Once the rocket reaches apogee and the can drops, we will start the reefing mechanism and the collection of the data. Once the can hits the ground, we will go in the third stage, the recovery mode. And it will start making our beeping sounds to help with the recovery.
For collecting our data, on the left side you see the flowcharts. First we collect our data and save, and also we will transmit our data to the Yagi Uda antenna. On the right side you see a 3D map, how it would look like actually, or trajectory. But the slopes will tell us when the parachute actually is reefed, and how steeper the slope, how fast the gunset will descend, and also we can calculate the descent rate, velocity.
For our outreach, we have a Facebook, Instagram and YouTube page. On Facebook and Instagram we post every week a small update about the project. We also been featured in a local newspaper, and we participated in a stage reel at a public observatory, Astrolab Iris. Thanks for your attention.
Thank you. congrats for your work. I have two questions. First one, is the shape of the parachute, is it automatically controlled by the program, or will you control it by distance?
The control will be time-based, so we will try to reef, so wind and unwind, and show the reefing 4 times during our 12-second descent. So it will be already in the code, so we won't have to do it manually.
Okay, thank you. And my second question is, what is the range of distant rate you are waiting for?